Welcome to Efiwe, excellence without stress.
Hi guys, we are back again. It's me, your favorite tutor, Miss Stella, and this is our continuous journey into excelling without stress in physics and in most of our science subjects. We're going to take another very important topic today, which is waves. It is a very broad topic, but very interesting and very easy. So, and today this is our table of contents, definition, classification and types of waves, properties of waves, terminologies in waves, plain progressive wave equation, and so on and so forth. So let's just dive in as quickly as possible. Definition of wave. Wave motion is the transfer of energy and momentum from one point of the medium to another point of the medium without actual transport of matter between the 2 points. So we're saying wave motion is just the transfer of energy. You can call it the transfer of a disturbance from one point to another without the actual movement of what is causing the wave. So that is what wave can be defined as. Wave motion is classified based on 1, the medium of propagation, 2, the dimensions in which a wave propagates energy, and also the energy transfer. So classification of waves. The first classification we're going to focus on is classification based on the medium of propagation. So we have different classes of waves, and today we're going to talk about each and every one of them. So the first one is mechanical waves. So what are mechanical waves? So the waves which require a material medium for their propagation are known as mechanical waves. That is, before you can see or before you can say this is mechanical wave, then there must be a medium of propagation. And that is what a mechanical wave is. For example of mechanical waves are water waves, sound waves, and I know you don't need to tell me the medium of propagation. When you say water waves, you already know that water is the medium, sound waves, spring waves, and waves of the turning fork. So these are all examples of mechanical waves. Mechanical waves are waves that requires a material medium for their propagation. That is, they need something, they need a mode, they need to pass through something before they can be propagated. So the other type of waves in this classification based on the mode of propagation is the electromagnetic waves. So electromagnetic waves are just the direct opposite of mechanical waves. Why? Because they do not need material medium for their propagation. So we say electromagnetic waves are those that do not require a material medium for their propagation. So they arise from the vibrations of electric and magnetic fields. The combination between electric field and magnetic field waves is called an electromagnetic waves. Examples of electromagnetic waves are light waves, X-ray, and the gamma ray, etc. Electromagnetic waves are a family of the wave spectrum. The members and their frequency ranges are as follows. So let's quickly talk about the differences between mechanical waves and electromagnetic waves. So just as I've explained in the previous slides, is the major difference between the two is just the fact that one requires material medium for its propagation, while the other does not require material medium for the propagation. So mechanical waves requires material medium, electromagnetic waves do not require medium. So electromagnetic waves travels through speed at the speed of light. It's just like the way the ray of the sun is reaching us without any material medium. So that is one of that can be regarded as an electromagnetic wave. So light waves are electromagnetic waves because they do not require material medium before they get to us. So they can pass through a vacuum. So another classification we're going to focus on today is based on the direction of propagation. The first one was based on the medium of propagation. This one now is based on the direction of propagation. And in this classification, we have two types. We have the transverse wave and we have the longitudinal waves. So how do we define the transverse wave? So the particles of the medium vibrate in a direction perpendicular to the direction of propagation of the wave. The region of maximum upward displacement is called the crest region, while the downward displacement is called the trough. Transverse wave motion occurs only through a medium which has rigidity, modulus, or shape of observation. For example, the string wave. So you can see this one is moving up and down, and this place is called the trough, the crest, and the lower part is called the trough, and this is the direction of the wave. So this one is moving perpendicular to the direction of the wave. So the wave is moving this way, while the wave itself is moving in the upward direction. So let's go to the longitudinal wave. The particles of the medium vibrate about their equilibrium position in a direction parallel to the direction of propagation of the wave, and that is what is called the longitudinal wave. Both of them are moving parallel to each other. So if it's moving in the horizontal direction, then the other ones will be moving in the horizontal direction, and that is the longitudinal wave. Longitudinal waves require a medium which only elasticity of volume or bulk modulus for its propagation. In this type of wave motion, the wave travels through a medium in the form of compression and rarefaction. So these points where it looks as if they are kind of squeezed together is called the compression, and this other part is called the rarefaction. So the region of high pressure is called the compression, that is this part, while the region of lesser or low pressure is called the rarefaction. So can you see now that the air molecules is moving in this direction and the wave also is moving in this direction? So we have already talked about this, the different types of waves. We have the mechanical wave. So the mechanical waves, which is a wave that need material medium for its propagation, can be divided into longitudinal wave and transverse wave. So while the electromagnetic waves, these are examples of electromagnetic waves. All these waves here do not require material medium for their propagation. The radio wave, the infrared, the ultraviolet, the gamma ray, X-ray, visible light, and microwave, they do not require material medium. But we have the sound wave, the water wave, they all require material medium for their propagation. So these are the major terminologies we are going to be seeing as we go through wave. Wave is a very, very broad topic, very, very broad, but all these terminologies will be used as frequently as possible. So we have the period. This is the time taken for an oscillating material to complete one oscillation. I know you remember what oscillation is. That is to and fro movement. So the time it takes for an oscillating material to complete one oscillation is called the period. And if you check this other side where my mouse is, you see that T, which is the period, is equals to 1 over the frequency. So let's go to frequency. What is frequency? It is the number of complete oscillation made in 1 second. So just as this formula has already told you that T is inversely proportional to the what? To the frequency. So the period and the frequency, they are proportional to each other, and frequency is the number of complete oscillations made in 1 second. So if you made any oscillation you make in each second refers to the what? To the frequency. So let's go to another one, which is the wavelength. Wavelength is the distance between two nearest or two successive crests or two nearest troughs. So don't worry, you will see, you know, I showed you what crest and trough was before. I said this is a crest and this is a trough. So the distance between this point and this point is one wavelength. While and also the distance between this point and this point is also another wavelength. So the distance between two successive crests or two successive trough is called the wavelength. So speed, just as you know, we already know what speed is. Basically, speed is what? This distance over time. But when it comes to wave, speed is wavelength over period. That is what the speed is. So if you want to say the speed of a wave, the speed is measured as wavelength divided by the period. So amplitude is the maximum displacement from the rest position of the wave. Why displacement is just like the distance measured from the rest position upward and to the right is positive, downward and to the left is negative. So these are the important formulas we need to actually know. You must be very, very conversant with all these formula. V is equals to F lambda. That formula will be used in almost all the wave topics we are going to use. So what is our V? Our V is the speed of the wave, lambda is the wavelength, while F is the frequency. And don't forget T, which is the period. We already know that T is equals to 1 over F. And also, simultaneously, F is also equals to what? 1 over T. That's very, very simple. So T, which is the period, is time divided by the cycles, while f also is just the opposite of the period, which is cycles divided by time. So examples, let's just quickly solve some examples so that we can apply the formulas we have learned. So the first question says, the wavelength of a water wave is 10 centimeters. We know that water wave is a mechanical wave and the frequency is 15 hertz. The first question is, what is the distance between the successive crests of the wave? The second question says, what is the speed of the wave? And the third one says, what is the period of the wave? So the first question says, what is the distance between the successive crests of the wave? Just as I explained to you, I said wavelength is what? The distance between two successive crests and two successive troughs. So this question is just trying to know if you remember what a wavelength is. So since it says the wavelength of a water wave is 10 centimeters, and they are not asking you that what is the distance between the successive crests of the wave. So they are just asking that what is the wavelength, and that is what? 10 centimeters. So that is answer. So let's go to the next question. What is the speed of the wave? So I've already solved it here. I don't think we need to go to our board since it's just very easy. So our V is what? F lambda. You know, F is our frequency and lambda is our wavelength. I already told you that anytime you have questions in physics, the best thing is to write out your parameters, then you think of the right or the best formula to use in solving it. So you have V is equals to F lambda. So from what we were given, our F is what? 15 hertz, and our lambda is what? 10. So getting our V, which is the speed of the wave, is so simple. It's just 15 multiplied by 10, and that gave us 150 centimeter, or we convert it to the standard unit, which is meter per second. So 150 centimeter to meter is just 150 divided by 100, which is going to give you 1.5 meter per second. And the last question is now, what is the period of the wave? So easy. We already know that there's a relationship between period and frequency. So we have our frequency, and now we are looking for the period. So T is just 1/15, which is equal to 0.067 seconds. As easy and simple as that. So the next question says, the number of waves that pass by in a second is known as the wave's what? So the A, velocity, B, speed, C, frequency, D, wavelength. So we already know that the number of complete oscillation per second is the frequency. So the answer here is what? Our frequency. So the next question says, the power of a wave comes from the wave's dash. Amplitude, B, speed, C, frequency, D, wavelength. I know that the answer is what? Amplitude, as the amplitude is the highest displacement of the wave. Let me just quickly show you the part of the amplitude if you've forgotten. So this point here is the amplitude. So that's the highest displacement. So I know that if two children are holding a string, two maybe 10-year-old and two 3-year-old, if they're holding a string, the amplitude of the way they're going to swing that string is going to be different. So this highest displacement is called the amplitude, and that was the question we tried to. They said the power of a wave come from the wave's what? Amplitude. So let's continue. So this is another very important and simple aspect of wave, which is the plane progressive wave equation. So this equation will be used to solve so many questions. So the equation of a plane progressive wave is given by y is of x comma t is equals to a sine kx minus wt plus phi. So this is our k, which is the wave constant, and this our w, which is omega. Here, W is the displacement of the wave, A is the amplitude of the wave, K is the wave number, W is the angular frequency, X is the position of the wave, T is the time, and omega is the phase constant. So all this will be used in our plane progressive wave equation. And this is it here. I'm going to go to the board and we're going to break down the plane progressive equation. So this is the beginning of it, and from this we can derive a lot. We can get so many equations just from this first one. We have that our y is equals to a sine wt plus or minus kx. We already know that w is the angular frequency, k is the wave constant. So let's just go to our board and try to get how we got this remaining equation, because here we have that our y is equals to a sine 2 pi over lambda vt minus x, and so on and so forth. So let's go to the board. we're going to try to derive the remaining equation. So we said that y, we said y is equals to a sine wt plus or minus kx. So I told you that w is the angular frequency, k is the wave constant. So from here now we can get another formula, because we have that our w is equals to what? 2 pi f. I know we all know that formula. And our k is equals to 2 pi over lambda. So putting this into our equation, we have, the equation started with a is equals to a sine wt plus or minus kx. But we can also put w as 2 pi f, and we can also put k as 2 pi over lambda. So our y would then become what? A sine. So instead of putting w, what are we going to put? We're going to put our 2 pi, then we're going to have ft, then plus or minus what? K will now be represented with what? 2 pi over lambda, then the x will be there. So this is another equation. This is so important because there are so many questions in plane progressive waves, and they will just write it anyway. But if you know how to derive equations, you'll be able to solve any one. So we have this now. We can also bring out our 2 pi because we have 2 pi in both of them. So we can have that our y is equals to a sine. We can factorize 2 pi out. A sine. So let's bring out the 2 pi. So this one will become what? Ft, right? Plus or minus x over lambda, because we factorized 2 pi out. So recall also that from v is equals to f lambda. F can also be equals to what? V over what? Over lambda. So if we represent that in the equation also, we can have that our y will be equals to what? A sine 2 pi. Then instead of writing f, we're going to write what? V over lambda. Then we have the t. Then plus or minus x over what? Over lambda. So we've derived so many equations for the plane progressive wave. So let's go back to our slide and see. So you see now. So from here now, we said a is equals to a sine 2 pi ft minus 2 pi x over lambda. Just as I explained, I represented this f, which is f is equals to v over lambda. We represented the f with what? V over lambda. So or y is equals to a sine 2 pi over lambda vt minus x. You know how we did that? We just factorized the 2 pi outside, 2 pi over lambda, because we have lambda here, we have lambda here, so we can factorize the 2 pi over lambda out. Then we're going to have vt minus x, and so on and so forth. So this is just so simple. Look at another way. Look another one here. Vt over lambda, bringing back the lambda, and so on and so forth. So let's just go to the next equation. So a wave has a period of 0.25 seconds. How many oscillations will pass a given point each second? What do we call this property? I think we've answered this question in the previous question. This one is telling us that we have a period of 0.25 seconds. So they are now asking for how many oscillations. You know that there's a relationship between period and frequency. So if they're asking you that how many oscillations, you know that it's just your period. So let's just write that out. Let's go to our board. They gave us a period of 0.25 seconds. They're not asking us for the oscillations, which is basically the what? The frequency. So we have so they gave us the period. Recall that we have that our t is equals to 1 over f, and they gave us the t to be equals to 0.25 seconds. So to get our f is just what? 1 divided by what? 1 divided by t, which is equals to 1 divided by 0.25. And we are good to go. So if we want to just quickly get it, we can say this one multiplied by 1,000, this one multiplied by 1,000, to just quickly divide it. So this. So we have 1,000 divided by 10, and which is going to give us 100 Hertz. But let's use our calculator to get that. But I guess we are right because we've multiplied it out. So let's go to the next question. So our frequency is 100. So they said a wave has a period of 0.25 seconds. How many oscillations will pass a given point each second? What do we call this property? That's just our frequency, as easy as that. So the next question says the equation of a progressive wave is given by y is equals to 5 sine 100 pi t minus 100 pi x, where y and x are in meter and t is in second. So let's just quickly go to the board. So we have y is equals to, don't worry, we'll write it down. Control and delete. We have that y is equals to, don't forget our first formula, y is equals to a sine wt plus or minus what, kx. So having that now, we're going to just write down the equation that we were given. So we have what, 5 sine 100 pi t. So we have y is equals to 5 sine bracket 100 pi t. So let's put plus or minus what, 0.4 pi x. So 0.4 pi x. So now from this equation now, it is so simple. Don't forget what we said the other time. We said that our w was equals to what, 2 pi f, right? And we said our k was equals to what, 2 pi over lambda. So we can put this into the equation, right? So we can have that our y is equals to a sine 2 pi ft plus or minus 2 pi over lambda x. Then we close the bracket. So now looking at this now, 5 is our amplitude. Remember that. W is our angular frequency, k is our wave constant. So having this at the front, our t is our time and x is the distance. So what is our 5? So the first question says what was the first question we were asked? First question says the amplitude of the wave. Okay. Let's just get it ourselves. The wavelength, the frequency, and the velocity. So for this now, we want to get the amplitude. So we know which one is correct. The amplitude, the frequency, the wavelength. Amplitude, the frequency, the wavelength. And what's the last one? Amplitude, wavelength, frequency, and the velocity. So we'll check which one is correct. They're asking us for the right statement, but we're going to get it ourselves. So from here now, what is our amplitude? That one is the easiest, just from the equation. A represents the amplitude. So our amplitude is what? Our amplitude is 5 meters. So that one is checked already. So they now asked again, what is the frequency? So this kind of equation, what you need to do is to always vary them. You check this point. Where do you have frequency? You have 2 pi ft here, you have 100 pi t here. So this is the part where we have what? Frequency. So we're going to equate 2 pi ft to the 100 pi t to get our frequency. So let's do that very quickly. So we have that 2 pi ft is equals to what? 100 pi t. That's the importance of the plane progressive wave equation. You equate it to the equation you are given. So we know what to do first. Our pi, let me show it like that. So this pi will cancel the other pi here. So what else? What are we having left? We're having 2 ft, right? Is equals to what? 100 t. What else can cancel? T can cancel t, right? So we have 2f. So our f is now going to be 100 divided by 2. So our f is equals to 50 what? Hertz. So we have checked the first one. Amplitude checked. Frequency checked. So which other one? Let's go to the next one. Our wavelength. So just as you know already, k and 2 pi lambda over x gives 2 pi over lambda is our k. So we are going to equate this to the 0.4 pi x. So let's do that. So we have, let me just do something like this. Okay, so we have 2 pi over lambda x is equals to 0.4 pi x. So you know, just the same way, x will cancel x, pi we cancel what? Pi. So what else do we have? So we have 2 over lambda is equals to 0.4, right? So our lambda is just equal to 2 over what? 0.4. So let's multiply each of them. We can multiply this one by 100, this one too by 100 to easily get our equation. So we have 200 divided by what? 40, and that's equals to what? 5. So our wavelength, which is lambda, let me just write lambda, Control Z. Hope this is not too rough. So our lambda is also equal to what? 5 meter. So then we have our what? The last one is to get our velocity. Don't forget, from the normal wave equation, we have that v, which is the speed of the wave, is equals to what? F and what? Lambda. And we already have our F. What is our F? Our F is equals to 50. Our lambda is equals to 5, right? So, and that's going to give us what? 250 meters per second. So, and that is all. So now we have the amplitude. Let's put it there and go and check which one is correct. Our amplitude was 5 meter. Our frequency was 50 hertz. Our wavelength was 5 meter. And our velocity was 250 meter per second. So let's go and check. We're asked that which of them is correct. So he said the amplitude of the wave is 5 meter. I guess, okay, that's checked. Very correct. The other one says the wavelength of the wave is 5 meter. Correct. And the other one said the frequency of the wave is 50 hertz. Wow. And the velocity of the wave is what? 250 meter per second. The question asks which of the following statements are correct. So basically the 4 statements are correct, and we have calculated to check that all of them are correct. Okay, so just in the same way we solved the first question, let's go and solve this other question. It says a plane progressive wave is represented by the equation this, where y is displacement in meter, t is in second, and x is distance from a fixed origin in meters. So now we have to look for the frequency, the wavelength, the speed of the wave respectively. So let's go to our board to solve it just the same way. This question will be solved by you. Having solved question B and C, you should easily be able to solve this question. So let's go to our board and solve it. So we have this already. So we have that our y is equals to 0.1 sine 200 pi t minus 200 pi x. So we have to look for the amplitude, frequency, wavelength, and the velocity. So let's just write our wave equation very quickly. Our progressive wave equation. We know that our progressive wave equation is equals to, okay, y is equals to a sine 2 pi ft minus 2 pi x over lambda. Yes. So now we are going to do the same thing we did in the previous question. We're just going to equate. So this is where our f is. So we can get f from this place. This is where our lambda is. We can get our lambda from here. So let's do that quickly. So we have 2 pi ft is equals to what? 200 pi t. So we're going to cancel the pi. We're going to cancel the t and the t. So what are we left with? We are left with 2f is equals to 200. So our f is 200 over 2. F is equals to 100 hours. So please always put your unit anytime you are solving. So we've solved for our frequency. So have we solved for our amplitude? No. So what is our amplitude? Amplitude is just very easy. It's just from the question. Recall that A is the amplitude. So our amplitude A is what? 0.1 meter. So let's not forget that. That's our amplitude. So, and it's in meter because it's a displacement. Amplitude is the highest displacement of the wave. So that's the amplitude. So let's go to the next one. We've checked for frequency, right? So now the next one is to check for our wavelength. So in the same vein, we're going to equate this to this. So we have 2 pi x over lambda to be equal to what? 200 pi x. So same thing, we're going to cancel x, I'm going to cancel the pi. So we have 2 over lambda is equals to what? 20. Yes, 20. So our lambda is going to be equals to 2 over 20, which is equals to 1 over 10. So we have it that also in meter. So let's go to the next question. So we have that. So let's get our velocity. So you recall that your v is equals to what? F multiplied by what? Lambda. So what was our f? Our f was 100. And what was our lambda? Our lambda was 1 over 10. So let's just cancel that. 10 in 10 is 10. So our v is just equals to what? 10 meter per second. You see how easy it is to solve. So we've gotten our wavelength and we've gotten our velocity. I'm sure you understand everything we did. So we are done with that. So you should be able to do the last question, which says this is just the same thing. Even from here, you know your amplitude already, you know the formula you are going to use, and so on and so forth. So let's continue. So now we are going to the properties of waves. The properties of waves. So the first property we are going to look at today is the reflection. The reflection. So when a wave meets a barrier in its path, it turns back. If the barrier is plane, the angle of incidence is equal to the angle of reflection. So look at it now. This was the wave. It was coming and it came and it met a reflecting surface. So that was what happened. So it came here and it did what? It bounced back. So we have incident ray and the reflected ray, and later you're going to learn the law of reflection. She just simply says the incident ray, the reflected ray, and the normal all lie on the same plane. So this is what has happened. So the wave was coming, the light wave was coming, it's the surface and it bounced back, and that is what this reflection is talking about. Reflecting it, the same thing. So automatically the I here, which is the angle of incidence, is equal to R, which is the angle of reflection. So when a wave meets a barrier in its path, this is the barrier they are talking about, it turns back. So ideally this wave was supposed to be moving in a straight line. If not for this barrier, it would have continued its journey, but because of this barrier, it had to what? Go back, and that was the reflection. So they said when a wave meets a barrier in its path, it turns back. If the barrier is plane, the angle of incidence is equal to the angle of reflection. This is called reflection. All waves exhibit reflection. The production of echo is due to the reflection of sound waves. The formation of an image in a mirror is due to the reflection of light waves. So that's exactly what we're going to talk about later. So refraction, another property of waves. So when a wave moves from one medium to another, its direction may change at the boundary between the two media. This is called refraction. The change in direction is due to a change in wave velocity as it passes from one medium to another. As you can see, this was in air. This light ray was actually coming from air, but when it entered water, which is another medium, there was a difference. That is what is called refraction. So basically, refraction occurs between two mediums, between two medias. It can't be one, it's two media. So when a wave moves from one medium to another, its direction may change at the boundary between the two media. So this thing will change at this point. When the incident ray was coming, it came straight like this, but can you see the angle that is different? The angle of incidence here is bigger than the angle of what? Refraction. So that's what this is talking about. So the change in direction is due to a change in wave velocity as it passes from one medium to another. So that is all about the refraction. So let's go to another property, which is interference. When two waves, so these are the waves they're talking about, when two waves moving along different paths meet and intersect, interference takes place. So that's it. When two waves moving along different paths meet and intersect, interference takes place. There are two types of interference. If when the two waves interact, they reinforce each other, that is, the combined amplitude is greater than any one of the two waves, the interaction is called a constructive interference. What that means is, maybe when this wave was coming, it was having maybe 5 meters of amplitude and the other one was having 2, and when two of them combined, it became 7. So that is constructive interference. Constructive. Look at each of the waves. This was the amplitude of this one, this was the amplitude, but when two of them combined together, look at the amplitude now. The amplitude became higher, and that is what is called the constructive interference. So And if on the other hand the interaction makes the wave to cancel out, like look at it now, this one was neutralized, this is complete, this one is partial destructive interference, this one is complete. At this point the amplitude is there is no more movement here, the amplitude has been neutralized. And if on the other hand the interaction makes the waves to cancel out each other, then the interaction is called destructive interference. So that's all about interference. Then diffraction. Diffraction is the bending. So the ability of a wave to bend around the edge of an obstacle. So I told you that light travels in a straight line. So at this point the light was coming with a force, but when it got to this point, it noticed that the obstacle here has just a very little entrance. So what will it do? It will bend around the obstacle, and that is what is called what? Diffraction. So the ability of a wave to bend around the edge of an obstacle or to spread around a small opening, this is the wave coming, and when it got here it what? Spread, and that is what is called the diffraction. So diffraction of a wave depends on the size of the aperture relative to the wavelength of the wave. For instance, doors and windows are big apertures that can cause the diffraction of sound waves, but too big to cause diffraction of light waves. So the bending of light wave around an obstacle is what is called the diffraction. So polarization of light. A plane polarization of light means the fluctuations or a vibration that is considered to vibrate only in one plane. So that is plane polarization of light. And what are the applications? Polarized cameras, production of three-dimensional films, sunglasses to reduce the intensity of light, and also determination of concentration of sugar solution. So these are the applications of plane polarization of light. So, and this is your assignment. So if the particles of the medium are vibrating to and fro in the same direction of energy transport, then the wave is a dash wave. We've done all of that in the previous listing. Thank you. Am I done?